Light flickers on the low ceiling. A horn is visible, or is it a tusk? Antlers, huge antlers, diverge and reach across the narrow cave. A vast herd of animals comes into view: deer, horses, bison, and amongst them stranger creatures, beasts long dead in this part of the world. Aurochs stretch along the walls, whilst giant deer are stalked by prides of cave lions. The prehistoric people of Lascaux in modern-day France had come to these caves for generations, layering images of fear and wonder on top of one another like graffiti, whose meaning and significance only they could say. These elaborate caves contain no dates, no indication of when they were created, yet the modern-day absence of aurochs, giant deer, and cave lions hints at a great age, a time when these exotic animals roamed the valleys around Lascaux. Today, carbon dating has revealed that these talented artists lived around 17,000 years ago, during the Upper Paleolithic, a time of great struggle. For much of the world was in the grip of an ice age, the likes of which humanity had never seen before. Things had been cold on Earth, with ice caps at the poles and chilly northern winters for most of human history, but about 26,500 years ago, it took a turn for the worse. Average temperatures plummeted to around 6 degrees Celsius colder than today, and ice sheets grew and extended down from the Arctic Circle to the middle of Europe and the North American continent. Around a quarter of the world's land surface was totally covered in ice, and sea level dropped 125 meters lower than it is now. This period, known to scientists as the last glacial maximum, saw the northern hemisphere transformed, making survival tough for the Paleolithic humans who called it home. These glacial conditions created cold and dry weather, with strong winds blowing dust into the atmosphere but little rainfall to rain it back out. Deep red sunsets would be reflected from the icy permafrost and tundra that spread across Europe, as fur-clad bands of early humans roamed back and forth across the edge of the ice sheet, stalking long-extinct monsters. Life in the Ice Age was hard, but Lascaux was a refuge for these people, a sheltered spot to regroup and reflect on their hunting victories and losses. Of course, many other bands of humans may have retreated south, where temperatures were warmer and the ice was a distant memory. We don't know if the Lascaux tribes survived through the last glacial maximum, but certainly the human race clung on in the refuges away from the ice. This was because, whilst the last ice age was certainly intense, it wasn't global. There were plenty of places on Earth that weren't frozen. The grip of this 5,000-year winter may have been hard for humanity, but there is evidence for much harder times in Earth's history. Times when there would have been no escape from the ice at all. Times when it wasn't even certain if the Earth would be able to break free. For just over 500 million years before the Lascaux made their home, a spectacular event may have struck our world. An event known informally by climate scientists today as Snowball Earth. But did these total global glaciations really happen? How could such extreme ice ages even occur? And what would they have meant for Earth and its precious, precarious life? The Cave of the 100 Mammoths is a fascinating cave system in France, covered with engravings and drawings of ancient mammoths. They ruled the earth at the same time as the Lascaux peoples, not only in France, but all over the world. And so, our documentary recommendation on Curiosity Stream this month is Ancient Yellowstone, Mammoth Country, a fascinating dive into the fertile hunting grounds for paleontologists atop the ancient supervolcano. Ancient Yellowstone is a great series in general, and just the tip of the iceberg when it comes to the thousands of documentaries available on CuriosityStream on topics ranging from ancient history to deep space. CuriosityStream is also a bargain at less than $20 a year and has fantastic new shows popping up every week. So go to curiositystream.com/history of the earth to sign up. And using the promo code History of the Earth will save you 25%, bringing a full year down to $14.99, just over $1 a month. Thanks to CuriosityStream for supporting education on YouTube. Douglas Mawson trudges on and on through the snow flurries and blistering Antarctic wind. Sliding one foot in front of the other, his skis slice through the fresh snow and his poles impale the drifts. He barely feels the weight of the sled behind him anymore. After 3 years in the field, it is as much a part of his body as his own arms or legs. But now, on the last stretch of his final journey, Mawson is numb, inside and out. 2 months earlier, in November 1912, the Australian geologist had set out with 2 other explorers, Xavier Mertz and Belgrave Ninnis, to map the coastline of the Australian portion of Antarctica. The expedition had gone well for the first 5 weeks, with the 3 men and a raft of sled dogs speeding across the white, featureless expanse. But disaster had struck when Ninnis's sled fell through the snow covering a crevasse, and he, his dogs, and more than half of the party's supplies disappeared into the heart of the glacier. Ninnis was never found, and Mawson and Mertz turned back immediately. With so few provisions for themselves and the remaining huskies, the pair were forced to eat their own dogs. Exhausted, sick, broken in mind and spirit, but with still more than 100 miles to go before base camp, Mertz took a turn for the worse. He became delirious, biting off the tip of his own finger, raging violently and suffering seizures before falling into a coma and dying. It later transpired that he had been poisoned by vitamin A from the sled dog's livers. Mawson was alone, but had no choice to continue or face death himself. He eventually made the lonely journey back to his camp, but his bad luck followed him back. He finally arrived to discover that the ship due to take him home had already left just a few hours earlier, forcing him to spend another winter on the ice, with more than enough time to mourn his lost companions. Despite these horrors, upon returning home, Mawson was awarded with a knighthood, and his venture had uncovered such a wealth of biological and geological data that it took 30 years to fully unfold. Though he did later return to Antarctica, Mawson spent much of the rest of his career studying the geology of his native Australia. As professor of geology at the University of Adelaide, he had ample opportunity to consider the geological history of the entire country. And there was perhaps no one more suited to interpret the mysterious rocks that researchers and prospectors were discovering. Across a swathe of the sun-baked continent, there appeared to be almost 1,000 miles of glacial sediments. They were clearly out of place, but they were also incredibly ancient, dating back to the Neoproterozoic period, long before the evolution of animals. Mawson doubtless drew on both his geological and Antarctic experience when he made a remarkable suggestion. Perhaps, he said, the whole of Australia had once been entombed in ice, in some kind of global glaciation. How else could you explain the freezing of a place as hot as Australia, if not by the freezing of the entire world? Mawson's geological and glaciological reasoning were sound, but they failed to account for one thing: continental drift. As the theories of continental drift and subsequently plate tectonics gained ground, they helped geologists to solve the puzzle of these seemingly incongruous deposits. Accepting that the continental masses traveled across the face of the Earth as crustal plates scraped, collided, were destroyed and made anew, permitted places like Australia to become glaciated without the need for a worldwide freeze. During the Neoproterozoic, it turned out, Australia simply lay closer to the poles, and was therefore more likely to experience normal polar conditions. Plate tectonics may have undermined Mawson's conclusions, but that wasn't the end for his ideas. As geologists learned to reconstruct the shuffling of continents through geological time, new sedimentary conundrums began to present themselves. For one, glacial deposits have been found in Greenland and on the Arctic island of Svalbard. On the surface, this is perhaps not surprising, since both of these places experience long polar nights and year-round freezing conditions. But these particular deposits date from around 650 million years ago, when tectonic reconstructions suggest that Svalbard and Greenland lay at tropical latitudes. Ancient ice in Australia may not indicate a global glacier, but ancient ice on Greenland does. But it's not just these two places that hint at an extraordinary Neoproterozoic glaciation. All over the world, geologists use elemental isotopes and local relationships to find the age of their rocks. And they use the alignment of ferromagnetic minerals like hematite and magnetite to the Earth's magnetic field to find the latitudes at which these rocks were formed. Finally, they use clues in the rocks themselves to reconstruct the paleo environment, and by extension, the paleoclimate at that particular location. Researchers began to find characteristically glacial deposits from the late Neoproterozoic worldwide. They include chaotic, unsorted sediments known as tillites, which are created by the action of glaciers as they churn up existing rock and deposit it. There are also drop stones, large cobbles or pebbles that appear to have been dropped from above into much finer layered sediment. Without having to invoke mysterious rock-slinging deities, these anomalies can be explained by melting icebergs dropping their sediment load far out to sea. Passing glaciers can also polish rock surfaces and leave long, straight scratches known as striations, and lakes that form from glacial meltwater record accumulate, finely layered sediments at their bottoms called varves, which reveal the seasonal ebb and flow of melting waters. All of these features have been found in rocks from the late Neoproterozoic, and most importantly, regardless of the latitude in which they were formed. Dropstones, varves, and tillites from near the equator lead to the inescapable conclusion that there was ice here, and the planet must have looked very different to today. Not only that, but late Neoproterozoic deposits contain some rare and unique rock types that are hard to explain without drastic climatic and oceanographic transformation. Banded iron formations, which disappeared from the planet some 1.5 billion years earlier, now make their reappearance in rocks from 700 million years ago. Their presence implies oceans that were occasionally anoxic, something that would only be possible in the Neoproterozoic waters if something was stopping gases from being exchanged between the atmosphere and ocean. Something, perhaps, like an immense, uninterrupted ice sheet that covered the global ocean like a shell. Finally, in a stroke of remarkable geological synchronicity, researchers have consistently found a single type of rock laid down worldwide directly above the widespread glacial deposits. No one is sure exactly how or why the cap carbonates formed all around the world, all at the same time, but a leading explanation involves the sudden influx of new material from the land surface into an ocean that had become strongly acidic with carbonic acid. Alternatively, the cap carbonates may just represent the moment the oceans breathed again after a long and constricting global freeze. And so, all of these pieces of geological evidence seem to point to the same remarkable conclusion. In the late Neoproterozoic, starting around 750 million years ago, the Earth experienced an intense ice age that saw widespread freezing of the land and ocean. A global glaciation that caused ice to extend from the poles right down to the tropics, perhaps even meeting at the equator. An icehouse world that transformed the Earth from a watery paradise to a barren, almost lifeless ball of ice. And what's more, this probably didn't happen once, but up to 4 times in quick succession, right up until the dawn of animal life. American geologist Joseph Kirschvink aptly named these global glaciations Snowball Earths, for the way they turned our diverse blue marble into nothing more than a featureless white orb. But the period of geological time in which many of these extreme events occur is known as the Cryogenian, after the Greek for frost. Now that Neoproterozoic rocks have been studied in detail, the individual glaciations are named after the rock formations where they were first identified. The Sturtian glaciation is the oldest, occurring between 750 and 660 million years ago. It's followed shortly after by the Marinoan Ice Age from 650 to 635 million years ago. Records suggest that a very brief global glaciation followed 579 million years ago, and the final Snowball Earth is known as the Baconurian glaciation, and it marks the very end of the Proterozoic period, lasting from 549 to 530 million years ago. It's worth noting that these are not the first times that the planet has been plunged into icy purgatory. Around 2.5 billion years ago, the Earth was put into a 300 million year long deep freeze as a result of the Great Oxygenation event, and the atmospheric changes that followed. But more than 1,500 million years have passed since then, and the Neoproterozoic Earth is a very different world. Life has become complex, cooperative, and the stakes are higher than ever. Just how hard will it be to survive on a cryogenian Earth? An icy comet speeds through the solar system on a slingshot course towards the Sun. Flung on this fateful trajectory millions of years before from its home in the distant Kuiper Belt, it has swung and looped around its star nearly 1 million times. But the lonely comet's days are numbered. This may well be its last stellar tour. With every approach, the sun's heat evaporates some of its icy mantle, sending it streaming behind in a glorious, rainbow-lit tail. And the once magnificent icy asteroid is now but a shadow of its former self. Nevertheless, on it flies. It sails past Neptune and Uranus, cold ice giants lurking in the dark, onwards and inwards to Saturn, girdled by rings, and looming Jupiter with its unruly moons. As it pierces through the relative clutter of the rocky asteroid belt, the sun's warmth begins to grow, and the comet begins to glow. On it goes into the inner solar system and past the already dry and dusty Mars. It's still 700 million years before humanity will evolve to recognize its reddish glow in the night sky. But Mars has already lost its life-giving atmosphere and oceans to the unforgiving solar wind. Only a little water remains, frozen at the red planet's poles. Closer still to the sun and the melting comet's days are numbered. The Earth's single gigantic moon is its penultimate flyby, and as the Earth itself grows larger in the comet's sights, and the sun's heat eats away at the comet's core, 2 frozen bodies glow as brightly as one another. On one side of the sky, an icy asteroid is about to meet its end, and on the Earth, an entire icy planet. There is no end in sight. It sits squarely in the warmth of the sun's habitable zone, and yet not a drop of liquid water is to be seen. In the clear night skies above this Snowball Earth, the comet disintegrates and evaporates into a superheated vapor. But on the planet's surface, the big freeze continues on, a crushing global winter with no easy way out. From the air, the blindingly sunlit dayside is cast into sharp relief by its shadowed night. separated by a smooth terminus uninterrupted by either mountain or valley. But the planet's night side is not completely dark. The bright white surface reflects the star and moonlight, giving an entire hemisphere an eerie grey glow. Yet it's almost impossible to see the planet spin as the featureless globe slides beneath its shadows. Time on Earth during the Cryogenian is just as undifferentiated as its geography. Seasons pass, winter to summer, but with no visible change on the surface. All remains white. Years, decades, and millennia pass through cycles of solar activity and subtle changes in Earth's orbit and spin. But still, there is no visible change on the surface. It's easy to lose track of time, and before you know it, 90 million years have passed. It is only when on the surface that it's possible to differentiate between icy land and icy ocean. The sea ice appears as an endless, smooth expanse, interrupted only by larger icebergs trapped and frozen in place. But approaching the hidden shoreline, the ice cracks and heaves in chaotic slow motion, the result of tidal forces bulging the still liquid ocean beneath many meters of ice. There are long, flat, white coastal plains that then rise to a rolling rocky landscape. But all is smoothed and softened by the indiscriminating blanket of snow and ice. Only occasionally is a sharp rocky ridge or peak visible, blown free of snow and ice by the unforgiving wind. Indeed, wind is likely the only weather that this frozen ball will experience. With temperatures at the equator as low as those on modern-day Antarctica, there's no spare energy in the atmosphere for brewing storms or rain clouds. Ice covers every surface, becoming a barrier to evaporation and making it extremely difficult to pump water vapor into the air. Without clouds through the night, there's little retention of heat close to the surface, and at night especially, the temperatures plummet even further. It is unfathomably dry and cold, but still, the wind blows. From warmer dayside to colder nightside, or from extremely cold mountaintops to only very cold shorelines, the wind blows, uninterrupted across the featureless surface. It whips loose snow and ice crystals into a sparkling ice mist, and rivers of powder blue across the ground. It would be quite beautiful if it weren't so deadly. For the surface is most certainly inhospitable to life. Atop the snow and ice, there is none of the water that every life form needs to survive. And since snow and ice cover the entire globe, there would seem to be nowhere left for Earth's fragile inhabitants to cling on. And yet, cling on they do. The ever-innovative biological metabolism is capable of endless variations. By 750 million years ago, bacteria, algae, and the unicellular ancestors of animals had already adapted to inhabit almost every corner of the oceans and inland waters, and were beginning to creep their way onto land from the shores too. So when the Earth froze over, life may have lost most of its territory, but it was able to persist in whatever stronghold, whatever refugia it might find. While on the grand global scale the Earth is featurelessly frozen, there will always be some fine-scale variation, some tiny cracks in the facade that life can exploit. Beneath the thick oceanic ice shelf, the oceans are not frozen to the bottom. They might be pitch black, they might be anoxic and stagnant, but there are microbes that can still eke out an existence on such meager rations. Life's ancestral refuge still exists at the very bottom of these stagnant oceans too. Hydrothermal vents pump warm, mineral-rich water out onto the sea floor, and they are colonized by chemolith autotrophs, able to get all they need from the minerals that build the underwater volcanic chimneys. There are opportunities for the photosynthesizers too, even though the freezing temperatures at the sunlit surface are at first grossly incompatible with these organisms' need for light. But again, cracks in the facade leave space for algae to scrape by. Where the sea ice has heaved and cracked and changed its shape a million times, pockets of water could become trapped close enough to the surface to receive a faint, life-giving glimmer. Similarly, as the days and seasons come and go, some ice inevitably thins and cracks when exposed to the unforgiving glare of the midday or midsummer sun, producing small areas of translucency or even open water. It would freeze again when the sun sets or winter rolls around, but life has taken its chance and can sleep out the coldest times in sun-fattened dormancy. Microbial life is even able to build its own habitable microcosm on the surface of the ice, creating and expanding dark, water-filled pits that riddled the ice surface like Swiss cheese. Known as cryoconites, these vertical holes begin to form when the sunlight seizes up the dark color of dust grains trapped within the ice, warming it up more than its surroundings, which allows it to melt the ice around it. As the hole expands, it captures more of the warming dust, and it's colonized by dark-colored snow algae that accelerate the warming and melting effect. Indeed, even when the world is at its coldest, these cryoconites are proof that life not only finds a way, but helps to engineer its own way too. And so, as remarkable as it may seem, even as Earth plunged into an apparently eternal ice age, it was not accompanied by a mass extinction of life. There's no evidence of any great dying or of the loss of any major branch of the tree of life. Unlike the last deep freeze more than 1.5 billion years earlier, where scientists believe up to 99% of all living things on the planet perished, organisms seem to have muddled through unscathed. A remarkable demonstration of what 1.5 billion years of evolution and diversification can do for life's resilience in the face of seemingly impossible odds. Planet Earth today is in the midst of a climate crisis. Since the Industrial Revolution, we have been pumping carbon dioxide and greenhouse gases into the atmosphere at a remarkable rate. This revolution transformed how we live, work, and play, and fossil fuels are now as invisibly essential to our lives as water is to fish. But the carbon they release doesn't belong in our atmosphere. It was locked away hundreds of millions of years ago as part of a natural cycle playing out on geological timescales. We have broken the wheel for our own immediate gain and are now suffering the consequences. Overwhelming scientific evidence now points to a single conclusion: that human activity is causing the Earth to warm at its fastest rate for tens of millions of years. While this in itself is bad news, things get much worse when we consider the effects of this unprecedented anthropogenic warming. As the planet warms, it gets harder for ice to remain covering the poles. Every year during the Arctic summer, the sea ice retreats further than it did before, and soon we might expect the watery North Pole to be completely exposed. But changes aren't just happening at sea. The land surfaces in the Arctic are also frozen as permafrost, down many hundreds of meters in places. Ice turns soft soil into sediment as hard as concrete, impenetrable to water and air. Much of northern Canada, northern Europe, and Siberia are gripped by a year-round permafrost that stunts and stifles any organism that would choose to live here. But global warming is eating away at this permafrost too. All over the northern hemisphere, the thickness of this frozen layer is diminishing, thawing, and in the process relinquishing an unexpectedly damaging cargo. Methane that was created as dead plants and animals decayed within the permafrost is now able to escape into the atmosphere. And methane is 25 times more potent as a heat-trapping greenhouse gas than carbon dioxide. Its release into the air only helps the planet to warm up more, causing more melting of the Arctic permafrost, more release of methane, more warming, and so on. This so-called positive feedback is a vicious, escalating spiral that could see the already dire effects of human-induced climate change suddenly become catastrophically worse. The Arctic alone is thought to contain 1,500 billion tons of carbon, which is almost twice the amount of greenhouse gases already in the atmosphere. For context, human activity over the last 250 years has increased the amount of these gases by just 50%, but the positive feedback loop in the Arctic could see it jump by 200% in mid-decades. Scientists suspect that we have already passed the tipping point for this climatic death spiral, and the best we can do now is figure out how to weather the storm. 60 years ago, in the 1960s, humanity was as yet blissfully unaware of the coming climatic apocalypse. With the development of modern meteorological methods, scientists were just beginning to understand the interconnections of weather and climate across the globe, and were assembling some of the first climatic models that predicted long-term trends in environmental conditions worldwide. During this meteorological renaissance, a Soviet climate scientist named Mikhail Budiko, perhaps inspired by the brutal winters that assailed his home city of Leningrad, began considering the effects of different degrees of ice cover on the global climate. As anyone who has considered dressing in a hot country will attest, light-colored materials reflect the sun's radiation more effectively than dark-colored ones. The dark, fathomless depths of the ocean soak up 94% of what the sun dishes out, whereas the same ocean, covered by ice, will reflect up to 70% of that radiation. This so-called albedo effect means that cold, ice-covered areas tend to stay cold, because they bounce back the one thing that can warm them up. It is the beginning of a positive feedback loop, and Budiko's model assembled the mathematics to discover how far that spiraling rabbit hole went. His models showed that if temperatures on Earth dropped enough to allow ice cover to reach latitudes of around 25 to 30 degrees north and south, level with Texas, Egypt and South Africa, then the cooling albedo effect would outweigh the warmth from the remaining ocean, forcing ice to advance all the way to the equator. And so external temperature drivers don't have to be as extreme as one might imagine, and the Earth's own escalating feedback would take it the rest of the way. Budiko's reasoning and mathematics were sound, but he was quick to doubt his own work. The model suggested that once ice reached the equator, then the completely ice-covered globe would reach a new thermal equilibrium, and losing any mechanism by which it might warm up again. Essentially, if ice ever reached a latitude of 30 degrees, then his work suggested the Earth would be plunged into an inescapable global ice age, from which there could be no thermodynamic reprieve. As a result, he squarely dismissed the idea that this had ever happened in Earth's history, for if it had, we would still be living on Snowball Earth. Nevertheless, there is strong geological evidence for tropical glacial deposits during the Neoproterozoic, and with positive feedback in the loop, we can reasonably expect that to mean ice extended all the way to the equator. But Budiko's model does offer a little help to scientists as they search for reasons for the global snowball. We only need to find mechanisms that can create a tropical ice age, rather than an equatorial one. Although average global temperatures for much of the Cryogenian would have hovered around minus 50 degrees Celsius, we are only looking for a mechanism that can drive average temperatures down to near freezing point. And for that, there are a few viable options. The first Snowball Earth, also known as the Huronian glaciation around 2.4 billion years ago, was likely caused by a sudden and catastrophic change in the Earth's atmospheric composition. The appearance of organisms capable of making energy by oxygenic photosynthesis saw oxygen begin to replace greenhouse gases in the atmosphere. Photosynthetic algae consumed carbon dioxide and emitted oxygen, which in turn reacted with any methane in the air, turning it into the much less potent carbon dioxide, which in turn became fuel for more photosynthesis. It was this intrinsic change in the Earth's heat balance, in how much heat the atmosphere was able to trap that saw global temperatures drop and then, as a result of positive feedback, plummet. A similar situation could have occurred during the Cryogenian, although the mechanism for atmospheric transformation is harder to pin down. Perhaps a particularly productive time for photosynthetic life saw an uncommonly large amount of carbon dioxide pulled out of the atmosphere. Or perhaps a particular configuration of land masses was conducive to intense weathering that consumed carbon dioxide through chemical rather than biological means. However, there is little evidence in the rock record of either biological or chemical drawdown. If Earth's levels of insulating carbon dioxide suddenly dropped, then they did so without leaving a conclusive trace. If there is no evidence for intrinsic long-term changes to trigger a Snowball Earth, then perhaps the cause was more acute, in the form of a sudden and extreme change in incoming solar radiation. Modern scientists believe that a relatively short-lived event has the capacity to trigger extreme planetary cooling, providing it's intense enough. Perhaps those changes came from outside the Earth itself, as the Sun went through a particularly quiet period with much reduced activity. Or a combination of orbital changes that sees the planet's tilt and orbital path subtly tweaked to produce intense polar winters. Alternatively, a reduction of solar radiation could have come from within. An eruption of an immense supervolcano, the size of Yellowstone or larger, would release so much ash and reflective gases into the atmosphere that they would encircle the globe and block solar rays for many years to come. The planet would be plunged into a dim nuclear winter, and by the time the dust has cleared, the positive feedback is well underway. One final piece of the puzzle seems to be the distribution of continents across the Earth's surface, and there is a growing body of evidence that suggests that a large supercontinent close to the equator is a necessity if you are to end up with a frozen Snowball Earth. In general, continents are cooler and more reflective than the darkness of the open ocean, so they could help to accelerate and exacerbate the cooling process. But tropical continents go one step further. Normally, the weathering of land surfaces pulls carbon dioxide out of the air and so tends to reduce the global warmth by nibbling away at the greenhouse effect. It is the beginning of a stabilizing negative feedback that keeps conditions within certain narrow bands. When global temperatures drop below a certain level, the land becomes cold and the rate of weathering here slows down. There is less carbon dioxide being removed from the atmosphere, allowing the greenhouse effect to bloom and warm the planet once again. However, when there is land at the tropics, this stabilizing negative feedback has less hold over the global climate. Land that is exposed at tropical latitude is much more likely to continue to be weathered, even as global temperatures fall. So temperatures are dropping, but so are levels of insulating carbon dioxide. There is no negative feedback here, and the cooling can continue uninterrupted. It's a compelling thermodynamic theory, except for one important detail. For all other serious glaciations through Earth's history, there has been land at the poles, providing a surface on which ice can grow. Was there land at the poles or at the equator at the beginning of the Cryogenian? Unfortunately, conclusive reconstructions are difficult because of a lack of suitable sediment. And so, with more and more evidence that it did in fact happen, there is one big question that we need to answer. It is clear that this was not terminal. Indeed, a few million years after these events, the Cambrian explosion took place, a remarkable unparalleled diversification of life on Earth, an event clearly impossible on a planet covered with ice from pole to equator. We need to find an explanation for how the world recovered. Just how did the Snowball Earth end? Professor Joseph Kirschvink has made a name for himself as the real-life Iron Man. For more than 30 years, he has walked the crowded Caltech campus, contemplating the many things we stand to learn by studying magnetic materials, what they can tell us about biology, the history of life, and the history of the Earth itself. It was he who first suggested that banded iron formations might come about through a wide-scale global glaciation that effectively cut off ocean circulation, and in doing so, he was the first to coin the term Snowball Earth. And yet, unlike Michael Boudico, who foresaw apocalypse in positive feedback loops, Kirschvink was not so disturbed by the consequences of such a glaciation. Climate models can only tell you so much, he reasoned, and the Earth is a complex system that cannot be described by simple energy in, energy out. Nevertheless, the doomsday scenario predicted by Boudico had seized the imaginations of the public and scientists alike, and the theorized finality of a snowball Earth has been used to cast doubt on the theory. Indeed, to this day, there is disagreement in the scientific community as to the true extent of the Neoproterozoic glaciations. In order to make a claim for an extraordinary global ice event, there must be extraordinary evidence to support it. For one, the deposits must be unquestionably glacial. They must have definitely formed at low latitudes, and no other rock types should have formed at the same time. Unfortunately, 700 million years has been plenty of time for the clarity of that evidence to become obscured. Rocks that have been interpreted as glacial tills and iceberg dropstones could have formed by other means, with no need for ice at all. The paleomagnetic evidence that points to tropical latitudes for these rocks relies on the assumption that the Earth's magnetic field has always been what it is today. Had the magnetic poles wandered, then our sense of direction on the Neoproterozoic Earth would be irrevocably skewed. And finally, it is difficult to sort through the precise chronology of rocks that are found all over the world. Geologists usually use fossils that date to a very specific period of time, but in the Neoproterozoic, before the appearance of large-scale fossil groups, that precision just isn't available. And so, since none of this evidence is as solid as it could be, some researchers have suggested that the Neoproterozoic events were no different to other glacial periods in Earth's history, like the one we are living in right now. There is ice at the poles and at high elevations, and ice sheets wax and wane through the seasons and millennia. But there is no global freeze. Or, alternatively, an intermediate situation prevailed. Instead of a snowball, there may have been a slushball Earth, which saw ice extend down to subtropical latitudes while the equator remained ice-free, or with a band of thin, seasonal ice. This would have allowed some continuation of the hydrological cycle through these periods, and would help to explain some of the sedimentary rocks that seem to form in open water, or from moving ice. Indeed, it is important to remember here that the Earth is never static. The movement of tectonic plates across the Earth's crust could have periodically cracked the planet's icy shell, opening up pools of open water and offering some reprieve from the global freeze. However, even if ice came to hold our planet in its full grip, in a full-blown snowball Earth, Joseph Kirschvink still saw a way to escape. While the Earth is frozen, many of its dynamic processes and cycles come to a halt. Without open ocean, the water cycle ceases. Without life and water, the carbon cycle winds down to a mere trickle. But there is nothing about the freezing of the surface that stops the churning of the planet's interior. Tectonic cycling continues as crustal plates are created and destroyed at their margins, with accompanying earthquakes, vents, and volcanoes. And so this is where a chink in the snowball's icy armor appears. Active volcanoes continue to pump gases, including carbon dioxide and methane, into the atmosphere. Ordinarily, that carbon would be cycled back down into the Earth via the process of weathering, as acid rain forming from dissolved carbon dioxide eats away at the rocks. Or abundant life forms in the open ocean can draw it down and lock it away in the carbon of their bodies, or limestone of their shells. But without either of these cycles working efficiently, the carbon dioxide stays stuck in the atmosphere and builds up and up over millions of years of volcanic outgassing. We are currently witnessing what happens to the Earth when there is an excess of carbon dioxide in the atmosphere. The gas traps heat and warms the Earth via the greenhouse effect, and the more gas there is, the more effective this process is. And so, Joseph Kirschvink saw how a snowball Earth would eventually overbalance and collapse thanks to a supercharged ultra-greenhouse effect from accumulated volcanic gas. In time, the Earth sets itself right. Biology itself may have been a passenger through these wild swings in Earth's climate, but as with the Earth's eternal engine, the march of evolution never slows or sits still. While we can't know for sure how life scraped by through the intense cold and then sudden heating of the planet, it's fair to assume that it experienced some intense pressures to adapt and survive in new, extreme conditions. As such, it may well be that the Snowball Earth periods of the Neoproterozoic acted as evolutionary triggers, driving innovations that would come to shape the future of life on the Earth and the oceans. For instance, aquatic algae suffered through the global freeze as their shallow water habitats were iced over. But if they found a way to survive with a little less water, perhaps attaching to and feeding on the solid exposed tidal flats, then they would acquire all the adaptations necessary for taking the big future leap to becoming land plants. And so, the ends of the snowball periods coincide with some major biological revolutions. The enigmatic Ediacaran organisms, the first multicellular and truly macroscopic communities to appear, did so less than 10 million years after the end of the Gaskia glaciation, and the final Baikonurian glaciation may have actually contributed to one of the biggest radiations of life in the history of the planet, the Cambrian explosion of animals. The question still remains, however, as to how much the living component of our planet contributed to causing these glaciations in the first place. Ice ages may have kick-started evolution, but did evolutionary changes trigger the ice ages too? Certainly, the mechanism is there. If some adaptation suddenly allowed life to surge forward in its productivity, perhaps able to inhabit a new environmental niche or exploit a new, more efficient biochemical pathway, then it could have led to a tangible reduction in greenhouse gases, enough to trigger a snowball Earth. This is almost certainly how the first global Huronian ice age came about, and that Huronian period eventually saw the blossoming of eukaryotic life forms and the evolution of sex, so it's not unreasonable to imagine that the Cryogenian freezes could have been influenced by, and in turn influential to, the evolution of life. Although the Snowball Earths may have been some of the most testing times in our planet's history, promising unending global winter and the annihilation of Earth's most precious cargo, these big freezes have never yet followed through on their threats. In fact, when considered in the context of all geological time, they seem almost to be global resets, a chance for processes worldwide to stop and restart, perhaps beginning on a new course that would come to shape the world as we know it. It may be that, far from threatening our planet, Snowball Earths have been necessary for creating our modern, temperate Earth. You've been watching the entire history of the Earth. Don't forget to like and subscribe and leave a comment to tell us what you think. I will see you next time.